Hello, everyone. Thank you for joining us today. My name is Matt Perliman. I am a researcher and software developer on the System Advisor model team here at NREL. And today I will be giving a webinar on the marine energy performance models available within the System Advisor model. This is our second in a series of 5 webinars for this year. 2 weeks ago, we had a webinar on our merchant plant financial model. And in the subsequent weeks, we will have webinars on the new battery model features in SAM, the new community solar financial model, and electricity bill calculator updates. And recordings of all these webinars will be made available at the SAM website, that is sam.nrel.gov. For those of you joining us live today for our live webinar, we do invite you to submit your questions in the question box of the GoToWebinar application. A member of the SAM team will answer your question in chat, or they will bring it to my attention to answer during the webinar. Our agenda for today, I'll give a brief overview for some of you that may be newer to the System Advisor model about what SAM is. And then I'll break into an overview of our wave and tidal performance models and the LCOE Calculator attached as a financial calculation, upcoming work on those models and upcoming development. And then we'll move over from PowerPoint to the actual SAM window to give a live demonstration of how to use these models, go over some results and how to kind of visually view your results from your calculations. And we'll leave plenty of time at the end for additional Q&A as needed. So what is SAM? As I mentioned, the System Advisor model, otherwise known as SAM. SAM is free computer software developed and distributed by us here at NREL. And it is a unique software tool that combines detailed performance calculations on primarily renewable energy systems with detailed financial calculations for both front of the meter and behind the meter financial structures. So how does SAM do this? First, we combine resource data, in this case, wave resource or tidal resource data, with the design of your system. What type of wave energy converter or tidal energy converter are you using? What type of losses can you expect for your system to get you electricity values and energy production values that you then combine with cost, compensation, financing, and any incentives to get economic results. And this results in numerous results that you can view in terms of annual and monthly and hourly outputs and economic factors such as the LCOE. As I mentioned, SAM has many detailed financial models for both front of the meter and behind the meter systems. Today we'll be focused on the LCOE calculator, as this is the only financial model currently available for marine energy systems due to a lack of knowledge of what type of payment structures these systems would be operating under to this point. So jumping in to first our tidal performance model. So the first step in any renewable energy modeling project is defining your resource. So for the tidal performance model, this resource is defined by a velocity distribution, where we have on the vertical axis the probability distribution throughout the year in a percentage, and the x-axis different velocity values in meters per second. And this distribution must add up to 100% over the full year. And you can see in the table on the right how that would look in SAM. And we have some default values from the reference model project, which is a resource that aims to define some different wave energy and tidal energy converters. And that's where most of the defaults for these systems come from. Once you know your resource, then you can move into how are we producing power from those stream currents and stream velocity. And this is also defined from a distribution using the same velocity bin sizes as the resource distribution. You can define a kilowatt output for a single system at each velocity value, and then those would be matched up with the resource definitions to get the energy production over the full year. And again, these can be using defaults or imported as a CSV with comma separated values. So switching from the tidal model to the wave performance model. So defining wave resource is a little bit different, as there are two key parameters you have to consider: the significant wave height, which is the average of the wave heights in a given time, and the wave energy period, which is basically the reciprocal of the wave frequency. So on our vertical axis here, this is again a probability distribution considering two input variables. We have fixed bin sizes for the significant wave height in meters on the vertical axis. And on the horizontal axis, we have bin sizes for the wave energy period in seconds that are also fixed. And the grid in between these two axes defines the percentage of the year where you can find waves at that energy period and significant wave height for the given location. And as we'll get to when we get into SAM, there are some pre-built defaults from the reference model project and from different data sets. And the upcoming work, as opposed to defining a probability distribution, you can download data from the WPTO US wave data set as a time series definition, where we know the significant wave height and energy period every 3 hours. So rather than using a distribution throughout the year, you can just use your time series every 3 hours to know what your wave looks like for a given site. And information about that data set can be found on the AWS page that's hosting the data. And then the downloads that I'll get to when we get in SAM are coming from the NREL developer network. That's developer.nrel.gov, which has documentation on what's being pulled from this data and how to search it by latitude, longitude, and other aspects of it. So moving into the wave performance calculations after we define the resource. Similar to the resource, we have a matrix with the vertical axis being the same wave height bins and the horizontal axis being the energy period bins, with a kilowatt definition for a single device within each cross of the matrix. And this would apply for both the probability distribution values for resource or for the time series, where the probability matrix, you'd match up the different points along the matrix. And in the time series definitions for resource, you would find the closest match in this power matrix for each time series height and energy period in your file to calculate energy over the full year. So I want to clarify from this point forward, after you calculate resource and power for a single device for both the tidal and wave systems, the remaining inputs for the models are identical. So from everything I speak on going forward applies to both the tidal model and the wave performance model. So once you define your resource and your power for either, you have to define what is your array and your overall system capacity. You could do this by modeling only one single device. You can specify a desired system capacity overall, and Sam will do the calculations to try to figure out how many devices is needed to get closest to that number. Or you can specify the exact number of devices by saying how many rows do you have and how many devices. And then you can define some of your spacing parameters as well of where your system is located and how it is spaced, which affects the cable lengths calculations performed behind the scenes that then affect your electrical cost if you end up using a modeled cost value, which I will get to in a minute. Next, once you define your overall array, you define your percentage losses over the full year. This is done by putting in a single percentage value for different categories, such as array spacing, resource overprediction, and transmission, defining the annual losses due to these factors over the full year and summing them for a total loss. And again, our defaults for both the wave and tidal model are 2% transmission loss over the full year and 5% device downtime. And these come from, again, the reference model project that I mentioned earlier. Next, getting into our cost calculations. There are several different ways to define your cost, from simply a pure dollar amount to a dollar per kilowatt hour input. You can use modeled values based on the cost models to find from the reference model project, or you can enter detailed costs where then you go into subcategories to define costs that way based on the level of detail you know about your site. And I will get into some more detail once we get into the live demo, because it'll be easier to understand with a visual demonstration. The capital costs and operating costs that are calculated from these cost inputs are then passed into our levelized cost of energy calculator. For those not familiar, the levelized cost of energy, commonly referred to as LCOE, is the total project lifecycle cost expressed in cents per kilowatt hour of electricity generated over the system's lifetime. And this is done using the fixed charge rate, which is a either user input or calculated value based on the revenue per amount of investment required to cover the investment costs. So the LCOE basically uses the capital cost, operating cost per year, and your annual energy production to calculate a economic value that kind of gives an initial idea into the economic feasibility or performance of your project. Once you finish these calculations and run the SAM simulation, you can get many different results in terms of graphical outputs of LCOE contribution, heat maps that show the energy production as a function of either wave height and period or as a function of time, and tables showing your costs on different metrics. We also have two macros, which are additional code built into SAM to kind of help facilitate further analysis, that sends the results of your simulation to HTML files with interactive plotting tools to kind of look at your costs and performance in a different environment if that's more beneficial to you. The second macro compares two different cases within SAM. So if you have two different systems or two or more that you're looking to compare, you can compare the LCOE values by changing different inputs, and again, in the HTML format with interactive plotting tools. Within SAM, there's also a built-in reporting tool that can export the results into a PDF format with tables you can see on the left showing the cost breakdown for your system, along with the performance values and some graphical inputs as well, expressing the capital and operational expenditures as a percentage broken down by category. So that's what's in SAM right now for the most part. Future work to improve on these models that we're working on right now. I've mentioned the 3-hour time series data downloads, which I will demo in just a second. You can search that data set by latitude and longitude. There are 3 data sets for the West Coast, Atlantic Coast, and Hawaiian Coast, with 30 years of data from 1979, 2010. And there are options within SAM to download a single year of data, a multi-year range, or all 30 years of data, depending on your analysis. There are some new macros on the way as well, and updates to the electrical infrastructure cost modeling. Again, I mentioned earlier, those are dependent on the cable lengths calculated based on system spacing and your overall system capacity. Here is a quick visual of the download tool for the API downloads for the 3-hour time series data that I will now show as we move into our SAM walkthrough. So this might be a good point if there are any questions that came up that I can alleviate some confusion before we move into SAM.
Thanks, Matt. There aren't any questions in the question box. If you do have a question, please feel free to type it, and we'll do our best to answer it.
Okay, so moving into SAM, this is what you would see when you first open your SAM software. There's a welcome page giving updates about any current events, such as a webinar schedule, or any updates to the version you're using that you would need to install or have the option to install. I will then move over to our development version of SAM that doesn't have the welcome screen. This is the same thing, but there's just some upcoming development that we're working on, and everything, some of the stuff about the show is still in development and is subject to change, but it'll give you a good idea of what to expect. So starting from the welcome page, to start a wave performance model simulation, you'd want to start a new project. Here we have our list of different technologies that SAM is able to model. We have our marine energy tab, which contains both the wave and tidal options. So I'll click on wave. Next, you choose a financial structure. So the options here are our LCOE calculator that I mentioned earlier, or just to run the performance calculations with no cost inputs or anything. So we will go through the LCOE calculator, click OK. So once we get to this screen, you can see we have a variety of tabs on the left-hand side, starting with defining our wave resource, and then moving into defining our single device, defining our array, specifying our annual losses. Then we have 3 pages for the different categories of our capital or installation cost. 1 page to define our operating costs that are incurred every year. And then finally, a financial parameters tab to calculate our LCOE components. So SAM is built in with defaults for all of our inputs so that when you run a simulation by clicking simulate here at the bottom, you would get a result just to kind of see how the model is working. All the defaults, again, are based on primarily the reference model project inputs. Along the top bar here, you can see our case is untitled. We can give it a name by clicking this drop-down arrow and clicking rename. And you can add further cases to your file by simply clicking add and then adding more cases to your file. Like so. And when you would save this as a .sam file, .sam file, all of this information would be saved so that you can then open it again later and have all your cases here. So let's go starting from our resource data in our first tab here. So there are 2 different options here in the top left: frequency of occurrence, which is our probability distribution definitions, or our time series inputs. So if you're using a probability distribution, the main thing to look at is this matrix like I showed in the slides, where we have our wave height on the vertical axis, the wave period in the horizontal axis, and a percentage values in each box to kind of add up to 100% over the full year of the probability of waves at different heights throughout the year. And the values in this box are defined by selecting a option from this library. There are some built-in defaults from Sandia data, or there's the option to add folders to search for files that you put in yourself, that you can match the formatting of our built-in defaults by looking in the help documentation, which is always available in the top right corner, help. Switching over to our time series, which is still in development, we have another library of time series files and the option to add folders with your own time series files. And then a download tool to download data from that data set directly from within your SAM window. So this launches a separate window where you first select your data set, West Coast, Atlantic Coast, or Hawaii. Define your latitude and longitude, or the closest approximation to your site that you're looking for. And then the option to choose a single year from the drop-down list. Specify a range of values from 1979 anywhere to 2010, or the option to download all 30 years as well. You would choose the folder you want to download your files to, and then click OK. And then, assuming you selected a latitude and longitude that it actually has data available, that data would be downloaded and added to your library. Otherwise, there'd be help messages saying that the data is not available or that something went wrong with the downloads. Next, moving into our, I'm sorry, I don't know why this is moving a little slower than it was before, but we will work through it. Next, we move into our device definitions. What is the power output for a single device? We have some built-in defaults for power matrices from the reference model project in our library. There's also the option to import your own matrix from a CSV file. The syntax of how to make that CSV file are available in help. And again, the power matrix has a vertical column of wave height, a horizontal axis of energy period, and for each cross point in the matrix, we have a kilowatt rating for the single device. And the maximum output for this system, for example, is 286 kilowatts, which is our device rated power for this reference model 3. Next, moving into the array. What is our overall system capacity and how many devices are in our system? We can model a single device, specify our desired rated capacity, where we desire 500 kilowatts, and then the closest you can get to is if you use 2 devices, you'd have a rated capacity of 572 kilowatts. Or you can specify the exact number of devices, which is the default option, where we have an array of 100 devices in a 10 by 10 configuration with default spacing values from the reference model project that you could also change depending on how much you know about your system. Distance to shore and water depth, a new feature. If you are using a time series file, the distance to shore and water depth are part of the metadata from that time series dataset download. So you could fill in those values from your specific site. And you saw those update the cable lengths needed for the system, which can affect the system cost. And building in redundancy can also change your cost values as well. Your cable lengths, which then affect your cost. Next, we will move into the losses. I should clarify for people that aren't familiar with SAM, white inputs can be changed by the user, and blue values are calculated based on other inputs. So the help will give you any confusion about what these calculations come from. It can usually be found in the help window. In the sense that these change, if you use them from the file, then you can't change those. But if you change the box, then they turn to white, and you can put in your own values. And in this sense, these are calculated values based on these inputs. Moving on to losses, as I mentioned before, we have different categories for losses, such as array spacing losses, resource overprediction, transmission losses, array downtime losses, and other miscellaneous categories. We define an annual percentage loss for the overall system, sum up those values to a total losses of 7%. And again, these are the default values based on the reference model project. Now, moving into the definitions of your cost for your system. So we start with our device cost, which is a component of the overall capital cost. We have 3 subcategories under device cost. We have our structural assembly, our power takeoff system, and our mooring, foundational, and substructural cost components. So for each of these values, we have 4 different options for calculating costs. We can enter a dollars per kilowatt, where we will put in a user input that will then be multiplied by the overall system capacity to 50 times this number to times the rated array capacity value in this box to get to a category cost. We can enter a fixed dollar amount. And enter the cost that way. We can use the models from the reference model project to automatically calculate the structural assembly based on the system capacity mainly. And those equations, again, can be found on the documentation for the reference model project. And the newest feature is the use cost breakdown, which then opens up this dropdown for structural assembly cost breakdown, which then gives us different categories of costs related to structural assembly, subcomponent cost, that you can then enter dollar amounts for that will add up to the overall category cost. And for some subcategories, there are even further details you can put in depending on how much you know about your project and the different costs associated with it. And this structure applies across all of these different subcomponents. So power takeoff also has different subcategories that only become able to be edited once you use the use cost breakdown option. Otherwise, they are turned off basically so that you cannot change them. So yeah, these 4 options are available for basically all of these subcomponents. Or if you know very little details about your project, there is an override where you can put in a single dollar amount for your overall device cost, which is then summed with the number from overall balance of system cost and financing considerations for your project to end up with a overall installation cost value. I will put this back. So in some cases, there isn't as much detail, so the cost breakdown isn't available. So you would just put in a dollar amount for this one category. The same conditions apply for operating cost, where we have 4 different options again, and subcategories for the operational cost and the maintenance cost. And this total operations and maintenance cost value is also used in the LCOE calculation, which is found in our final tab, financial parameters, where the system capacity defined in our array tab is passed into this input. The capital cost, which I mentioned, is the sum of total device cost, total balance of system cost, and total financial cost is our overall capital cost, and our total operations and maintenance cost is passed into our fixed operating cost value. They give us our LCOE. We can enter a fixed charge rate. We have a default value, or you can enter your own if you know it. You can calculate it based on your analysis period, inflation rate, IRR, term debt, and other inputs. And that'll give us our overall LCOE calculation, which is the fixed charge rate times the capital cost value plus our fixed operating cost, and then divided by our annual energy production, which will be calculated once we hit simulate. So I will simulate that now, get our results. And here we have kind of a summary of our different results. We have our annual energy production, our LCOE value in cents per kilowatt hour, capacity factor, average power per device. The second table, we have different values for cost inputs. And 2 heat maps. In the case where you use time series wave resource data, we have energy production as a function of the wave height in a wave period, and also as a function of the hours of the day, where this is 3-hour data, and the day of the year. So you can see for the case we ran, there's an earlier in the year, there's some days that have some greater power production than in the middle of the year. You can see in the color scale, this is less. And so the middle of the year is kind of lower in this case. And a pie chart with the contributions of each cost category, where we have 4 different cost categories and their contribution to the overall LCOE calculation. There are other types of ways to look at your output data. So like time series graphs, where you can look at your power generation over the year. Tools to have 2 different outputs. And all of this is exportable to a PDF or an image, or you can send the data to Excel to work with it further. There are statistics about standard deviation and min and max for your data, monthly profiles for energy production and other 3-hour data outputs, probability distribution functions and cumulative distribution functions for your outputs. So those are just some of the ways that you can use your output data and kind of export them or look at them in SAM and get more analysis out of your system. And then now I can move into some of our advanced features located before the simulate, under the simulate button, focusing now specifically on the macros, because we have two marine energy specific macros, where the first, as I mentioned earlier, you can generate a HTML report for your system, where you can define these inputs to the best of your ability based on what you know about your system. I'm just going to put in some values here. Click Run Macro in this top corner. And this will make an HTML in your browser with information about your power matrix, your heat maps again, and some information about your system in an HTML format with interactive plotting tools to kind of make more out of your data. The second macro is to compare cases. So let's see how the costs are different based on what I changed in my first case to my second. I will run this, go back to my macros. The options here are to run all the cases in your file or only choose specific ones separated by a comma separated list based on the name of the case. And again, this will have bar plots showing the difference in the LCOE between the two cases and how those change from one case to the next. Another option to view your results is to come to the case and the drop-down arrow. You can create a report. We have built-in report templates that write to a PDF. You have the option to save it wherever you want, and then it'll open it in a window PDF viewer with information about your device, your resource, your array, and then detailed cost breakdown again in a table. And specifying how your cost was defined. Was it the modeled cost? Was it entered by the user? And those type of inputs. So just another way to view your data afterwards. I think that covers kind of the main way to use SAM for these models. If there are any questions, now would be a good time to go over that. Or
Thanks, Matt. There's a question about the reports for the tidal model. Apparently there's been some issues with the PDF report, I believe. I don't know if those were fixed in this as part of this work or if they're still there.
They are not fixed as of patch 2, but in the next release, I have fixed them in our development version, but it's just not in a release version yet, but those are being fixed. And we thank our users for finding those bugs in our report. Are there any other questions? Is there anything that was confusing that I should go over again or in more detail? Be happy to use our time to do some of that.
Here, Saul's requesting a demonstration of the stochastic tool.
Yeah, I'm not sure if we've built this to work with the WAV file yet because it's looking for a DNI or GHI input, but we could run it using we could have it theoretically run if you downloaded all 30 years of data from the downloads, then you could run the same simulation or vary the input variables over a range. Using like a normal distribution or different correlations between variables, and look at our outputs. I haven't tested this, so I'm not sure if it would work with 30 years of wave data yet, but that is something that we would like to do with these data sets in the future.
Yeah, I think at this point you could use this stochastic simulations to generate tables of values for, cost inputs or other parameters. But the weather file feature is designed for the solar models, so it wouldn't work for here. And there is a stochastic simulation video on the SAM website if you you can look at that to see how that feature works.
Yes, thanks, Paul. Sorry, I got focused on the weather file, but yes, the stochastic simulations will work for any inputs besides varying the weather file right now, and hopefully in the future we can have it work with the different weather files. But yeah, any cost inputs or spacing, array inputs, losses, I would advise setting up a stochastic simulation. Make sure you have the right options chosen to make these available. So make sure, like, if you want to vary prime mover costs, make sure that this is set to the right value. So if these drop-down boxes are based on 0, 1, 2, 3, so you'd want this option to be 3, or just set it in the UI beforehand so that you have this available, and changing the value will make a difference in the results. But yes, stochastic simulations for any of these cost inputs would work. And the video Paul mentioned is also helpful.
Great, thank you. So a question about the time frame for the releases. So Matt mentioned patch 2, which is our secret code for the current version of SAM, which is let's see, 11/29/2020, release 2, revision 2. That is currently out, but has the issue with the tidal report generator is in that version. There'll be a new version coming out this fall, probably in the November timeframe, and that new version will have a fix to that tidal report issue and these features that Matt is demonstrating today.
I can show that like I mentioned before, the tidal model, all these pages are the same except for the first two. So this is the definition of the tidal resource based on your velocity. These numbers can be whatever you want them to be, as long as they match on the converter page, and as long as they go in ascending order. And then you have a kilowatt definition at each velocity number matching the resource. I'm not sure, I don't think the macros are intended for the tidal model, so I wouldn't recommend trying to use those macros on the tidal model. But the report, once the next release comes out, the report will reflect the tidal versus the wave and the differences between those models. I'm happy to take more questions right now, and then if there's more questions in the future. For SAM specific things, feel free to reach out to me. And for marine energy specific, like technology questions, Elena Baca is an integral researcher for the water power technologies. So she would be a good person to ask about technology specific questions.
Thank you, Matt. And we did get another question here from Juan. In the case of a simulation of electricity production of different technologies, how can a sum of the different annual productions be made? So this sounds like a question about the combine cases macro, perhaps, which Matt will demonstrate here. But this is a macro that we've written that will take the annual or the hourly generation profile from 2 or more cases in a file and add them together to create a single generation profile that then is the input to a financial model. So you can model a project that combines the output of different systems.
Yeah, so I messed it up on the first part because to run the combined cases macro, you need 2 cases at least, or yeah, 2 cases with your power outputs you want to combine, and then you need a generic system case, which is located if you add a new case at the bottom, generic system, with whatever financial model you want. Oh, the array sizes for the time series aren't gonna match. So this might not work as is for that macro, but because it's using 3-hour data, it's a 2920 rather than an 8760 array of power values.
Can you
so that's
show
something I should?
Yeah, we need to investigate that. Can you show the power plant page?
Yes.
So the macro when it works properly, automatically populates this generation profile here with data from the summed outputs of the other cases in the file. So when it works properly, that's the way it should work. And then that generation profile is used with the financial parameters on your in this generic system case, so that you can calculate net present value and other financial metrics. I don't see other questions. Maybe we'll wait a minute or two in case someone's typing.
Yep. I will go back to this page to remind people of upcoming webinars after this one, if anybody's interested.
All right, well, if there aren't any other questions, I think we can wrap up. Thank you, Matt. We'll be posting a recording of this webinar on that events page that you went to to register. It'll be there for the next few months, and then it'll also be on the marine energy page of the SAM website. We'll post it there as well. So with that, I think we'll say goodbye. Thank you, Matt, and thanks everyone for participating in this webinar. We look forward to hearing from you soon at another webinar or on the SAM forum. Take care, everyone, and have a great rest of your day.